So there's two types of electricity: AC, alternating current, where you go up and down like a wave, and you can have different sockets with different waves that all equal or cancel out, and direct current, which is just one continuous. It's not a wave that goes up and down. AC current can somewhat travel farther distances in some materials. It's more complicated than that, and that's why it's widely used. It's easier to make some motors out of. Not all, because you can have it automatically turn stuff on and off. But it does not. And for like lights, it doesn't affect the lights too much, except for it might cause a little more flickering. However, for computers and a bunch of other devices, can't use it. Most household devices actually turn into AC first into DC. So, in this conversion, a ton of power is lost. Typically between 10 to 20% of power is lost to AC to DC. And you can also have the opposite. Sometimes you want to turn DC into AC for transmitting over long distances or for certain types of motors. There are DC motors. I just want to point that out also. So, how is this typically done? Well, the old way of doing it is you have something called diodes. And diodes work by let electricity in more easily one way than the other way. And by putting a bunch of these one-way valves, you can make it so that electricity is always flowing one way through a certain wire, and you connect them to wires. So I'm going to draw a simple diagram. Let's pretend that this is a diode. Diode and electricity comes in it goes back and forth in two directions, but out here only comes positive. Out here only comes positive. Then we have another connected to another diode that only negative comes out, and then negative, and that way we can split it. Now whenever you use diodes, the reason why you lose a lot of electricity is they don't instantaneously change back and forth. They don't instantaneously block the current. There's a little bit of current loss when it changes from positive to negative and negative to positive. Another loss occurs is that some charge builds up at each of the intersection, and those charge buildup can cause some loss of stuff like magnetic fields and stuff. Another loss is that the diodes itself have act a little bit as a resistor and lose electricity. And then another thing is, usually to make it more even, a capacitor is put. And a capacitor works by the reason why we put capacitors, with the simplest arrangement I put here, you're going to get bumps in your electricity. So one thing is only carrying positive charge wire, and one wire is only carrying negative, but there's bumpiness in that. It still goes up and down magnitude, positive and negative, like just ignoring all the wave that's below it, but you still have the wave going up and above. This can also cause a loss of efficiency, and to smooth out, you need a capacitor. Now, and also that going up and down can cause more loss because of magnetic interactions with other things. And remember that that changing electrical fields make magnetic fields, and that can actually zap away some electricity. So, on a totally separate note, it sounds like, we've started developing other people started developing the first at-home atomic clocks. And they only use only a couple hundred milliwatts, with about 120 is the best estimate I could make. And but some people say higher, some people say lower, but let's say order magnitude more, 1 centiwatt. These ones are going to give a huge advantage in computation because they can help sort out. A lot of computation depends on when something comes in and the latest update and accurate timing. And this includes any social media post, anything that updates, anything that's on a cloud network where different things working at different times. When you plug in cables, time is important because the more accurate time, the less you can see when signals are getting mixed up and stuff. Otherwise, you don't know if the signal is getting mixed up, because some things might take longer to travel, so stuff might get slightly out of order. But if you have a timestamp, you can fix that order much more accurately. So PLD is going to cause a revolution in computation. But here it also might cause a revolution in power supply. Let's say we use these atomic clocks to actually turn on and off the gates instead of using these diodes and stuff. Then you can have a more complete on and off gate that really does block out the flows and stuff, and eliminating a lot of the inefficiency, but lets in electricity a lot more than a normal gate does, a diode does, so you have a lot less resistor loss. And this whole meaning very, very efficient power transforming. You still have some difficulty in this region where it's about to change, and then you might need some diodes or something instead. But these diodes don't have to handle the current doing these big spikes here, or right here, where it's more regular. Just at the very intersection where the diodes have to be. And you can use cheaper diodes that switch on, that let more conductive there, with less loss. These, from a quick calculation is, let's say most atomic clocks are 120 milliwatts. But let's pretend that it's actually 1 centiwatt, about 8.5 times bigger. No, 120, sorry, that was way off. No, it's really about 8 1/3 times bigger. Don't know why I said way off. But let's say 1 centiwatt. That means then if you use 10, as long as you're using below 10 watts of power for your device, uses less than 10 watts of power, this is a more efficient setup, except for little diodes and stuff in between. But this will be a more efficient setup probably than if anything uses less than 10 watts of power. Now, what devices, how much do household devices use with power? Well, here's a picture of some typical ones. The only thing I can find is a clock radio using 10 watts of power. Everything else in the house really does use more power, even a blanket, fans, everything. Most light bulbs, most of the stuff is more than 100 watts of range of power. So this would be a very efficient switch right there. But it's probably even more efficient than what I'm saying. And the reason why I'm saying it's probably even more efficient was this clock, again, is very useful in computation in general. So why not use this one not only for computation? So if you use this clock and it's multitasking, it's acting as a power supply, and for the computation, you get more efficient computation and uses less power. And that power, and you're always going to use it in one use. So one use you kind of get rid of the power use. It's double tasking. Well, this is just some ideas on this particular one. Now, a further advantage is with the switches, it could also act as a DC to AC switch very well. And it could produce even more, and it could produce AC that's even more regular than AC coming out of your wall socket. And by more regular, I mean the phases are more matched up, so it's a more perfect wave. It has less little fluctuation where it speeds up or slows down or goes higher or lower, which can help a lot with consistency with devices and long lasting. Other things that it could do better is it could give you more unusual waveforms, which could be useful. So instead of having like a sine wave, which is like the normal wave you kind of see, you could have like a square wave where it looks like a square up fully or down fully, on and off, which is useful for some devices that need quick turn off or on and offs, and might be more useful for some motors actually. Well, thank you for listening. Please like and subscribe. It really helps the channel out. I'm trying to reach 1,000 subscribers in a year and 4,000 watch hours, which is really hard, but with your help, I think you can do it. Also, if you have any ideas for future videos, comments, or suggestions, please leave them in the comments section below. And by the way, the name of the new clock is the open source time card project. by Facebook. Again, thank you very much. Goodbye.